So I'm just gonna. Would I be able to share screen? I think you
Yeah,
may
sorry,
already
I
have.
need to make you the co-host. Just a
Oh, no
moment.
worries.
Okay. Yeah, so over to you, David. And
Fantastic. Oh no, that's not what I want.
so, sorry, just one moment. One thing I just want to point out, after David's talk, we'll have a session of question and answer. I'm going to ask some questions to Dave so that he can throw some light and help us get to learn more about him. And for those of you who are here, please prepare your questions. If you want, you can type in the chat, or if you want, you can unmute when the time comes for you to ask questions. Thank you.
Okay, cool. So can everyone see my screen?
Yes.
Yeah, cool. Awesome. So I'm going to be talking about sort of my journey. So how I uh, went from being a philosophy major to being on a machine learning, but I'm going to do it in the form of six sort of maxims or lessons. I mean, it's sort of tongue in cheek, but these are things that I wish I could have told myself when I was younger. So they may be useful for you. And I guess, so Gideon, with questions, like I'm happy if people want to ask questions during this, but maybe if you want to, yeah, whatever the policy is, I'm happy with. Oh, sorry. I think you're muted.
Sorry, I say it's totally fine however you want it. You're in
Okay.
chat.
Okay, cool. All right. Yeah, so feel free to ask during it. Just one thing that makes sometimes you forget by the end of the talk. So yeah, either is fine. Okay, cool. So I'm gonna start by talking about following your passion. So when I was in high school, for most of high school, I didn't really care too much at school. I wasn't particularly good at science. And something happened one day that actually I think kind of radically changed my life. I was just killing time in the library, and I stumbled upon this weird book. So it's a book called Archimedes' Revenge by Paul Hoffman, and it's basically a popular math book. And I was kind of intrigued by the cover. It's a giant Easter egg guarded by Mounties, and I kind of was like, okay, well, I have to know what's going on here. And it turned out to be a book about um, you know uh, various random topics in maths. So like prime numbers, cryptography, geometry, tessellations, things like that. And I was hooked. I thought this is actually kind of fun. It looked completely different from the maths I was doing in school. Um, and maybe that was one of the reasons that it was fun. It wasn't just like a bunch of kind of paint by numbers exercises. And I began scouring the library for other random books that seemed interesting. And the next one I found was something called How to Build a Time Machine by Paul Davies. So Paul Davies is a serious physicist, but he also is a great popularizer of physics. And this was kind of my entree into the weird world of relativity. Now these aren't technical books, but they were enough to whet my appetite. And even though I kind of sort of sucked at math, I was like, okay, maybe these are kind of cool things to learn more about. And the last book that had kind of a big impact on me in high school was Gödelische Bach. So a friend of mine recommended this, and it's sort of a bit of an insane book, and it's difficult to categorize, but um, it's a book about self-reference, basically, and it examines self-reference in sort of through three different lenses. One is through the lens of Gödel and his incompleteness theorem. So this is the lens of kind of mathematical logic. Um, Escher, the artist, and finally Bach, the composer, both of whom use self-reference in these sort of interesting aesthetic ways. So I love this book. I loved how weird it was, but it also got me interested in artificial intelligence, in logic and programming and things like that. Now, just to be clear, I wasn't formally studying any of these things, and I wasn't good at any of them. And in fact, my math grades were so bad that at the end of high school, I decided that I didn't want to study math or physics or any of those things. I was just going to go and do something involving words. So I went into law school, which was a terrible decision. It was not a good fit. Um, And after a year and a half, I dropped out. So there was partly it was just like it was a fancy prestigious course that a bunch of people had encouraged me to kind of go into because I had the grades for it, um, but it was not my bag. But I was also taking so in Australia you can do undergraduate law and you typically pair it with another degree as well. So I was doing arts, so the humanities, and I was studying philosophy and literature. And I enjoyed both of those. I like reading books, I liked words, and I liked kind of thinking deeply about things. And I think that in some ways the way I approached the maths and physics when I didn't have the kind of formal tooling was to sort of think about things philosophically. Um, so I ended up uh, essentially going into philosophy and literature, thinking that maybe that's what I would focus on instead. So the second lesson is, follow your passion or it will follow you. So I think the thing is when you have something that you're excited about and you don't pursue it, it doesn't go away typically. Typically, it sort of pops up in different forms and it kind of haunts you until you pay attention to it. So in my case, I was haunted by Goodell. So this is the Fred Goodell. He was probably the greatest logician since Aristotle. Um, and this is a particularly scary picture of him. But I continued to study Gödel, his incompleteness theorems, and things like that in my philosophy degree. So philosophy, this is where people study logic. You can do it in a math degree potentially, but it's much more typical to study it in a philosophy degree. So I was doing maths, um, and in fact, at the same time, this was another kind of lucky encounter. I went to the university bookstore one day, found this cheap copy of this weird looking textbook, a comprehensive textbook of classical mathematics by Griffiths and Hilton, who were two pure mathematicians who decided they would try their hand at an undergraduate math textbook. And the result is again, it's a bit insane. I found it very, very hard going, but I really liked the way that they did things. It seemed kind of logically rigorous. And this picture on the front is something called the Alexander Horn sphere, and it gives you an idea of like their vibe. Um, this is what they thought would be an appropriate thing to put on the front of their book about sets and calculus. It was it was a very steep learning curve, but I enjoyed it, and I think I began to convince myself that maybe I could do maths. And physics was also in the picture, so I ended up getting interested in the philosophy of physics and in particular the philosophy of time, and uh, wrote a senior thesis on uh, the reality of time or the present moment and so on, and special relativity. And it was an interesting question, but it was also really just kind of a chance for me to learn some physics that I wanted to learn. And at the end of this, I had a degree. I had a degree in philosophy, but I sort of had also gathered enough evidence to suggest that really the thing I was passionate about was maths and physics, and I should go study those. And so I went and got a second degree. Um, so the next lesson is that even if you follow your passion, right, which is I think a great thing to do, you may need to fine tune it. The fine tuning is not included. So I spent a lot of time trying to figure out what I actually wanted to study because math and physics is kind of a very broad that's not well defined. The first thing I discovered was that I did not like labs. I sucked at labs. I didn't understand the write-ups. I could never do them in time. Nothing ever worked. That didn't help. But the problem was me. The problem was not the labs. So experimental physics was out. Um, and I also had a fateful encounter with Fourier optics. So in second year, I took this course, which was about Fourier optics, which is a very, very beautiful subject, which also has some really nice applications. So it's sort of about, what happens if you play around with light and go beyond the sort of geometric optics regime and instead thinking about diffraction. In a way, it's an introduction to the basics of diffraction. Um, The course was really kind of a mixture of questions like this, like match the aperture to the diffraction pattern, and really horrible integrals. And I didn't get the essence or beauty of the subject until much later, definitely not in the course itself. And I decided, okay, that's it. I'm done with physics. I don't like experiments. I don't like the way that the theoretical stuff is taught. So I'm just going to focus on maths. And so what I ended up doing was pure maths. That seemed to be kind of close to the thing like learning about. It was beautiful. It was sort of pure in some sense. It was rigorous. And at the same time, I really like something that. So I'm a visual thinker, and so I sort of ended up focusing on geometry and topology and their relationship to algebra. So this is a picture of a knot in a sort of a donut with three holes, or sort of a pretzel thing. So I ended up getting a degree in pure maths. That was my focus, and started a graduate degree. And the idea I wanted to do mathematical physics. I wanted to do sort of geometry and topology as applied to mathematical physics, since it seemed that I would be able to learn some cool physics, but I'd be able to like use the math that I was interested in, or that I enjoyed. But I quickly ran into things like this. So I took a course on representation theory. Representation theory is like a super physical topic. The idea is like you have some symmetries. Your symmetries act on a space. Now, what do the symmetries look like? So typically, you think about matrix representations of symmetries. But if in the hands of mathematicians, or at least some mathematicians, it becomes this extremely dry, tedious, forbidding topic. And I quickly felt like, where's the physics? Where's the kind of physical reality that I can grasp and kind of draw and play around with? It was very formal. That partly reflected the university I was at, but it also reflected the math approach to it. So I decided to switch over to physics. And part of the reason was because while I was taking these graduate math courses, I was also taking graduate physics courses, just because I wanted to learn about them, and because I thought they'd be relevant. So I was taking quantum field theory, and here I knew what the diagrams represented. There was a very concrete physical reality to them. So this is a Feynman diagram, and general relativity. And general relativity was sort of even more striking. So, in quantum field theory, you have this sort of calculational tool, and you can sort of tell some stories about it. It has a nice interpretation. But in general relativity, Einstein's theory of gravity, the geometry is physics. They're the same thing. And that was really cool. I thought this idea that like the math and the physics were exactly the same, and it wasn't just a calculational tool, was really just kind of like, I don't know, surprising and striking. All right. So I switched over to a graduate degree in physics. And because I wanted to understand how to combine, I thought, uh, quantum field theory and general relativity are both interesting. What are some ways to do both of them? I ended up focusing on early universe cosmology and sort of particle physics in the early universe. And that was cool. I got so much interesting stuff, but I knew by the end of the project that it wasn't a great fit, or it wasn't the right fit. So lots of fine tuning needed to be done. Okay, so the next lesson is that reality converges in unexpected ways. So if you do a bunch of different things, they may end up coming together in ways that you don't expect. So while I was finishing my master's project and looking into sort of other things that I could do that seemed to involve, math, that seemed to involve physics, and particularly field theory and gravity. And I, learned about string theory, a lot of which seems very formal and sort of tedious and forbidding. And I didn't really want to study the formal, tedious, forbidding stuff. But I learned about something that kind of, it shocked me even more than relativity, general relativity being geometry. So I learned about something called the ADS-CFT correspondence. So ADS stands for anti-de Sitter, and CFT stands for conformal field theory. Apologies for the handwriting. Um, and it was this discovery in the 90s that you could describe the sort of quantum gravity. So you could sort of take Einstein's description of gravity, you could turn it into a sort of quantum mechanical description with a Hilbert space and interactions and so on. In this sort of negatively curved space, so space which kind of looks like one of these kind of Escher type pictures. You could describe it, but the interior could be described using the exterior of this cylinder. So like, if space looks like this, it's like this disk. Then over time, you sort of trace out this cylinder. And there's some physics you can do on the outside of the cylinder, which is called conformal field theory. And it's basically just field theory with a lot of symmetries. And that would be exactly equivalent to quantum gravity going on in the inside. So, maybe there's some strings in here, whatever. And that was shocking in itself. I thought that was extremely cool. And that was also the thing that most people in string theory were working on. So I thought, okay, maybe I should go to a PhD on that. I then discovered something even cooler, which was sort of a more recent discovery. So like 2006, 2007, something called the Ryu-Takanagi formula. And this is a kind of a very weird result. And the idea is that, the outside of this disk, which is sort of at the edge of space, is a quantum system. It's a quantum system which has lots of symmetries, but it's just a quantum system. And you can look at a subregion, so like an interval, if you like, and say, okay, well, if I have some quantum state of the overall system, I can sort of trace out the rest of this and then just get the state on A. So that will give me like a density matrix. The amount of entanglement between A and the rest of the system, which is also just essentially just the von Neumann entropy of rho of A, can be computed either on the boundary using quantum mechanics or field theory techniques technically, or in the middle of the cylinder using this. This thing is a minimal curve or a minimal surface more generally. That's why it's M for minimal. And you just find the length of that thing. You find the length of that thing. It's the shortest curve joining these two endpoints. And the length of that curve equals the entanglement entropy. And that seemed like too good to be true. And it was sort of like also like the kind of gateway drug to quantum information, because I was like, okay, well, what is entanglement entropy and what is all of this? So this is one way in which sort of reality converges in unexpected ways. Here we have like not only this ADS CFT correspondence, but this crazy connection between geometry and entanglement. So I thought that was very neat. So I came to UBC to study with somebody who works in this sort of thing. And what I focused on was black holes. So like you sort of put a black hole in the middle of this kind of hyperbolic disk, and now you want to study these things. And in particular, I was interested in this problem of the information paradox. So this is something that Stephen Hawking kind of proposed in 1975. Basically, he discovered that black holes aren't black, they glow. That means that they sort of leak information out slowly and eventually disappear. And the question is, well, what happened to the information that was inside? You could say it disappears, but then the universe doesn't evolve in a unitary way. And if you like quantum mechanics, you tend to think that closed systems are unitary. So something has to happen to the information. It has to somehow get out in the sort of glow of the black hole. And what we found is a really cool way in which these sort of minimal surfaces that appear in the Ryu-Takanagi surface actually allow for information to kind of escape from the black hole. So that was kind of neat, and again, it was kind of like it was a very cool sort of area to work on. And while I was doing this though, I was sort of exposed to all sorts of things. So all sorts of quantum-y things. So quantum information was a key part of it, but quantum computing actually is relevant as well. So like ideas from complexity theory, so circuit complexity, as well as the complexity theory from computer science were relevant. And here's a picture of an error correcting code. So this is like a toy model of ASTFT. There's a black hole in the middle for good measure. But there were a bunch of things that I kind of got to learn about that actually sort of weren't exactly string theory. They were more quantum computing and quantum information science. Okay. So the other way that reality converges in unexpected ways is when two different parts of your life, two seemingly unrelated parts of your life, kind of come together. So while I was studying, I was also doing outreach, and for a couple of years, I ran an outreach program called the UBC Physics Circle, which was a lot of fun. So it was basically just kind of like a fortnightly event for high school students from around the sort of lower mainland area to come and just learn about interesting topics, work on problems, and so on. And it was a chance for me to learn about crazy stuff. Like we studied everything from the length of the E. coli DNA to antimatter to nuclear explosions, and overall I had a blast. No pun intended. But one day we had some guests. We had people from Gearing Up, which is a really cool sort of electrical engineering based outreach program, come and do a demo on D-Wave. So it was sort of the quantum computer, a local quantum computer, and we solved some kind of Cubo problems and sent them off, them on the computer, and it was a lot of fun. And it kind of just got me thinking about it. I was like, well, there's groups in the area, like, this doesn't seem so different from some of the things that I'm studying in kind of string theory context. Maybe I should learn more about it. And I realized that I didn't know about anything about the algorithms or programs that actually get run on quantum computers. So through Gearing Up, I was kind of lucky. Like I got to work with Olivia Di Matteo. I went to a meeting one day, and she was like, "Hey, I'm looking for grad students to help me write a course." And I just put my hand up, even though I didn't know anything about quantum computing, and somehow it kind of worked out, and I got to teach myself about quantum computing. So this is a kind of janky graphic that I made for a very involved assignment about RSA and Shor's algorithm. So it was a lot of fun, and I got to learn just the sort of basics of quantum computing as distinct from quantum information theory, which is what I'd mostly done in my PhD. So unfortunately, that course never happened because Olivia left and went to a company called Xanadu. So I felt a bit sad about that because I'd put a lot of work into creating this material. But the next lesson is that nothing is wasted. So Olivia was at Xanadu, and she said, "Hey, you know what? You should come to a residency here. We have a school residency program, and you can continue working on the same sort of thing." And I was like, "Okay." So I went to Xanadu and did a 6-month residency, which was awesome. Well, actually, I should say it was mid-COVID, so I stayed in British Columbia and did a residency virtually, but it was still awesome. And I should say I will end, but Xanadu is actually accepting applications for the residency program like right now. And if you want to ask questions about that at the end or whenever, please do. Cool. So when I was doing my residency, I worked on something called the Xanadu Quantum Codebook, which Gideon also worked on. And it was heaps of fun. I got to continue doing the same thing. So learning about topics I didn't really know about, and then writing them up. So I Grover search and some stuff to do with oracles and just sort of the basic structure of quantum algorithms. And then finally, probably the most intense I worked on was Hamiltonian simulation, which again I just wanted to learn about. And it turns out is sort of like a very, very deep, very interesting problem. So it was a great experience. Excuse me. So I finished my residency, and then I went back to kind of just being a PhD student and kind of wrote up. And this is a depiction of my thesis, the eldritch and forbidding tome that is any PhD thesis. 2 people read it or something like that. But it was good. I finished, and then I had a kind of an interesting dilemma. So I applied for postdocs, so postdoctoral positions, and had some offers, and they were sort of more or less all in kind of ADS, CFT, string theory, high energy stuff. And on the other hand, I could continue working at Xanadu. So I was like very lucky to be in this position where I could kind of choose, but it was not an easy choice. The problem was I was told that in no uncertain terms that if I went into industry, I would be turning my back on an academic career in physics, not necessarily in other departments, but physics specifically. So that's apparently a sort of a maybe it's a convention or a cultural thing or whatever, but basically, if you go into industry, it's much harder to come back to physics. So if I wanted to go through the traditional academic route, that's what I needed to do. And on the other hand, a job at Xanadu would be fun. I sort of knew what it looked like. I kind of just enjoyed myself more than doing a PhD. And it also seemed to be like in some sense, a more exciting field. So ADS-CFT was really cool, but the big problem, the problem that I was most interested in, which was the information paradox, had kind of effectively been solved, like not by me, but by a bunch of different people while I was a PhD student. So I sort of had less interest in the area. And so ultimately I decided to go with passion. And again, it just sort of goes back to following your passion. I think this is good advice in general. But it did feel like there was a bit of a waste. I'd spent all of this time in string theory, like, what was the point of that? And I think just to return to the current lesson, it's like, I don't think anything is wasted. Whoever you are, whatever you do, those things you will bring with you to the problems that you work on. And I think particularly when you're working on like difficult problems, interesting problems, new problems, thinking differently, having a different tool set is actually going to help. It's going to distinguish you from other people. You're going to approach things in a slightly different way. You're going to have different analytic tools, and so on. So, in my case, it's like I studied philosophy, I studied pure mathematics, and now I studied string theory. And I could think of these all as wasted because I could have gone sort of directly into quantum computing. But actually, these things give me a very different outlook from the people around me. And that's good. So when I started at Xanadu, I was working on something called QHack, which is a sort of quantum computing hackathon. It's a lot of fun. The next one will be in February. So I would encourage you to kind of like sign up, and there's lots of prizes and fun stuff like that. And the main thing I was working on was coding challenges. So this was it was awesome. I kind of wrote sort of the majority of coding challenges, I think, and also kind of an overarching story. It was sort of the first time we'd done that, and that was kind of cool. So I also got to write a lot of crazy problems, but I'm not even going to describe what happens in the story because it's a bit ridiculous. But anyway, and these beautiful illustrations are by Tarek, the Xanadu graphic designer, who's awesome. But at the end of that, I was like, okay, this is fun, but it still felt like something was missing, and I sort of made the mistake, or the good, not a mistake in hindsight, but this was a good choice to attend some research meetings and just see what was going on. And I quickly realized that there were interesting things everywhere that people weren't thinking about. So, and this sort of brings me to the last lesson, which is that at the frontier, every direction is interesting. So you can kind of pick up a point on the horizon and start heading towards it, and you will find something cool. And because it's the frontier, there's so much room to find new things. And that's why it's, there's people are thinking about lots of important problems, but there's still important problems that other people aren't thinking about. So I started actually with some research projects in basically Hamiltonian simulation and algorithms of that nature, quantum phase estimation. And that's a very, very interesting area. It's very deep, lots of fun. But a position opened up with Maria Schultz's group, and so I joined her team in quantum machine learning. So quantum machine learning this is the thing that people say, it's the intersection between machine learning and quantum computing. That's not really super helpful so more concretely, like what is it? So the typical thing people do is say, okay, imagine that we have some data. So this is here that we want to embed, and we can somehow sort of encode this into a quantum circuit into, say, like our initial state. And then we have some gates, so alpha and beta. And these gates, we imagine, are parameter. So maybe it's a rotation angle or something. And you can kind of tune those. So now we have some dials that we can, or knobs that we can kind of turn to sort of change the output of this circuit, the measurement output. And finally, we can sort of turn these measurement outputs into a cost somehow. And then we get a little landscape, like an optimization landscape, and we will, typically try and choose alpha and beta to maximize or minimize this cost. Well, we want to minimize the cost. So, and that's usually what people do. And there's lots of interesting problems here. So, how do you sort of take the usual recipes? So gradient descent, for instance, in the case of a quantum circuit, it's not actually obvious how to do gradient descent. And so we have these things called parameter shift rules, which are very, very nice, very, very cute ways of kind of taking the same sort of optimization flow for classical machine learning and porting it over to quantum machine learning. So that's kind of what Penny Lane focuses on. So Penny Lane is sort of Xanadu's. Well, at this point, we would say it's our language for doing kind of quantum computing generally. It used to be sort of QML focused. But one of the things that Penny Lane does really well is differentiable programming generally. So it's maybe instead of just trying to kind of program these things in a differentiable way, so you can kind of be in descent, maybe you want to optimize the whole sort of control flow of your circuit. And Penny Lane is awesome for doing that. Okay, so, but this is a very thinking about these things. I think this is what I've kind of come to over the last 6 months. That this is a very specific way to do quantum machine learning, differentiable or parameterized circuits. That's great. Differentiating is great, but there are so many different ways that you could use quantum computers in machine learning. So this is a kind of a crazy diagram for how machine learning really works. So you have some parameters, so these dials here that you can use to kind of output some member of a model family. So basically, you have like a family of functions that's called a model, and your parameters just select some of that. That's something that goes into another machine, which samples from your function. So you pop in some X and you get out a Y, and you do that a bunch of times, and then you get some training set. Oops. So here's a training set. The training set then feeds into a loss function. That loss function is the thing that, or it's a cost function. It's the same thing. And then there's some feedback loop. You have like an optimizer here that goes sort of back and forth between your loss function and so on as you change the parameters. And eventually you kind of stop it and you spit out some guess of like optimal parameters for your model. And the reason I'm sort of, this is kind of like a very brief and kind of arcane description, but the point is that it's very complicated what goes on, and you could use a quantum computer at all of these different points. And this is kind of the cool thing. It's like, just to sort of drive home the point that every direction is interesting. There are lots of directions here that haven't been considered. Just because like there's people find something interesting and they all go in that direction, and then that's fine. Like, but there's lots and lots of cool things to think about in this realm, and we should be thinking about all of these different things. I think that's kind of the point that I wanted to make. Yeah, and that's it. So thanks to Gideon, Blackstone Quantum, the organizing committee, and all of you for listening. I just want to point out that the residency, if you want to have a look, this is the URL for the residency program. And if you want to chat, I'm obviously ask questions and stuff like that, but feel free to reach out. This is my email address. And yeah, thanks for listening.
Wow, I'm really inspired. Thank you so much, David. Your journey so far has been very inspirational, and I'm very happy that we have you as our guest speaker today. And Before I open up the floor for people to ask their question, I just have, let me start with this question. It is, you told us stories about how you got into philosophy and then your journey from philosophy to math and all that. So I just wanted to understand, when you were transitioning to your PhD, there was a move from Australia to Canada. What inspired that move? Just wanted to understand.
Yeah, that's a great question. So part of it was because I was really like dead set on doing something to do with the Ryu-Tachyon analogy formula and ADS-CFT. I just looked around and said, okay, who are the best people in the world for this? Where are they located? And they were located mostly in North America. So, and they were sort of concentrated on the West Coast and the East Coast. And then I looked at the cities and I was like, okay, how big are the groups? Who has, good ratings on rate my professors, like that kind of thing. And one of the people who was sort of highest up on this list was Mark Van Ransdonk, who was my PhD supervisor. And I was like, okay, well, I'm definitely applying to UBC. It sounds like it's a good school. It looks like a beautiful city, and it would be a really good research fit. So I applied to a bunch of places, but I heard back from UBC very early, so it made the decision much easier. But it was so it was kind of a question of like research and lifestyle fit, I think.
Okay, great. Thank you very much. So just wanted to ask you, because this is a common question that people ask me, what would your advice be to people who are trying to get into the PhD program in, let's say, in the field of quantum computing? What would you advise them? And in terms of choosing a supervisor, in terms of choosing school to, apply to?
Yeah, that's a great question. I think so. First of all, in terms of choosing a supervisor, it's not perfect, but looking at rate my professors just to see are they a good teacher is one useful metric, because people who are kind of bad teachers, or like people like students, like they never answer my emails or they're mean or whatever, those things will tend to transfer to their supervision. um, I mean, and also talking to graduate students, current or former graduate students of these potential supervisors is just, like typically they will. So my experience was that they're actually very open. So if there's problems, people will usually tell you, unless the supervisor is really, really bad. But then I think there'll be other kind of indications. So so that's for choosing supervisors. And you know, you want people who are doing good work, who write papers that you can understand. I mean, papers which, or maybe not that you can understand, but which seem understandable. So sometimes like a paper will come out, it will be like impossible to read, and it doesn't matter how much you learn about it, it's possible to read. It may be that you're just not going to. It's going to be difficult to kind of understand what they're talking about, just because they're bad at explaining things, or you have different cognitive styles, or something like that. So if you like their papers, I think that's a really good indicator. Um, And as for schools, it's hard. I think that choosing a good school is difficult, because when you're doing research, you're really working with the supervisor and the supervisor's kind of cohort of postdocs, students, whatever. So that in terms of like research stuff, that's kind of the key thing. But then you may want to just learn stuff, like you may want to take graduate courses in something like. And I think graduate courses can be a great way of say learning quantum computing, and particularly if the courses are good. So just seeing what the coursework kind of offerings are is I mean, and of course you can say it's always possible to like learn this stuff yourself, but it's much easier when somebody forces you to learn these things, I think. So yeah, that's just checking what the graduate program is like. And I do think that the lifestyle is really important. So finding a university where you're actually going to be happy to be for like a period of 2 years for a master's, or 5 years for a PhD, whatever it is, like that's really important.
All right, great. Thank you so much, Dave. I'm very happy for the answers. Does anyone have any question? I open up the floor to people.
All right, I do have a question. Can you hear me? Okay. Hi, David. Thanks so much for actually sharing your story with us. This was really a story of many twists, I would say. And yeah, and just to bring your attention to when you actually kind of pivoted to quantum computing, I wanted to find out how you actually did that, because I know your background was in physics, maths, philosophy, but you really didn't know a lot about quantum, let's say, quantum circuits, for example. So, how did you get started? What resources did you use? Because you mentioned you were going to develop a course. So I guess that was when you actually learned it. But like, what resources do you use to learn it? Um, 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 yeah. In general, what resources did you actually use to learn?
Great question. So like initially the main thing that I used was this textbook Nielsen and Chuang, and it's still like I think probably the best textbook for just covering like everything as of 2010 or something. I don't know. It's sort of like it covers all of the basics really, really well. Um, it's very it's very dry, and it is a bit out of date, or in the sense that a lot of stuff has happened since then. But I think for kind of learning, and not just the basics, but like I mean, it has so much material in it. Um, that was something I found really, really helpful. Then for some of the other stuff, let's see. Um, there's this book for something which is much less dry. Like I really like Scott Aronson's approach to things. So quantum computing since Democritus is really awesome. And he has like he's sort of it's very different. Like Nielsen and Chuang is sort of dry and careful and rigorous, and quantum like Scott Aronson is sort of like you know I mean he's an absolutely like brilliant guy. So when you look at his papers, in his papers actually, there's so many jokes and like that. They're a lot of fun, and actually I found that kind of complimentary. Um, and I mean, there's so many resources out there, but I think those are two really good places to kind of get a feeling for things.
Thanks. Just a follow-up, sorry for those other questions. So, and this are more kind of in science, getting the fundamentals, getting the details. So how about, let's say, getting some coding skills, for example, and doing some coding exercises, for example. So what platform did you use? I think one of the popular ones now it's IBM and Penalane. So what were your go-to?
Yeah. So when I was developing course material initially with Olivia, we were trying to write some coding exercises, and so I learned a little bit of Qiskit at that point in time, and which I liked. And then she was like, "Oh, you should learn Penny Lane." And I was like, "Okay, I just started playing around with it, but I didn't do that much. But in the residency, everything was Penny Lane. We were developing this quantum code book, which involves writing, as Gideon will know, the sometimes painful process of trying to figure out how to turn some like theoretical textbook stuff into like coding exercises. So like writing coding exercises is really hard, and it actually really teaches you I think in some ways it's harder than actually doing coding. It's because you have to kind of come up with it, you have to debug it. That was honestly that's what I spent most of my time on. Like there was that aspect of things, and that was a really good exercise. It's not a usual exercise though, and now so again, just to be a bit shameless, so the Penny Lane team has released this coding challenge platform. So you can actually go do year round these coding challenges. And okay, also this is kind of it's not a secret exactly, but there are the coding challenges from previous years of the Q hack. You can also find online, not on Penny Lane, or not on the Xanadu site, but on like just random GitHub repositories. If you look for them, you can find them, and people will have their solutions as well and stuff. Which for some reason we never release solutions. I still don't really understand why that's the case. But yeah, people will have their solutions as well. So that's really good because then you can check.
Yeah, thank you very much, David.
Thank you so much.
Yeah, there are some questions in the chat, but let's take the question from Habibullah before we move on to the chat. Yeah, go ahead, Habibullah. Are you there? Okay, Dave, I don't know if you
think
can
he's
speak.
muted.
Yeah, you are muted if you are speaking. Okay, Dave, you can take the questions in the chat so that we can cover some ground.
Cool.
There are two
Okay,
questions
so
I
yeah.
see. Yeah, the first one is, say, for quantum computing, what level of statistics do you need? And then the second one is, what is your advice for newcomers into the field of quantum computing, and what could you have done differently looking back now?
Okay, those are both great questions. So for quantum computing, I would say that just quantum computing itself, it really depends on what you want to focus on. So if you're doing, say you're working on like hardware or even just like simulations or algorithms which involve some complicated post-processing of measurements, then you need more statistics. You don't necessarily need like super advanced statistics, but you may need to do like if you know how to use you may need to like create some things in matplotlib and graph them and stuff like that. So like I think some practical along those lines, some practical data analysis can be helpful, but it's not necessary. If you're doing algorithms, if you're focusing on algorithms, like maybe you don't need any. It's sort of it really depends what you're doing. If you're doing quantum machine learning, on the other hand, you potentially need a lot, and you may need a lot of theoretical statistics. So one of the things when I was I didn't talk about this, but when I was doing a residency with Olivia, I also was kind of learning about some quantum machine learning stuff. So I was just dipping into it, not in any serious way. Excuse me. I was learning about like kernel methods. And so kernel methods is sort of the basis of support vector machines, which you may have heard of. But that's much more advanced statistics, much more advanced theoretical statistics, and it's very relevant to machine learning. It's kind of like or like old school machine learning, and I thought this was really beautiful. But it's you don't need to know about that unless you want to work on machine learning, and even if you work on machine learning, you may not end up using it. So I would say some level of practical data analysis is probably helpful. And then depending on what sort of stuff you want to do, more or less statistics maybe necessarily. Like, as an example, actually, I have a book. I have this book called Elements of Statistical Learning, which I read every time I want to feel like I don't know anything about statistics. And I've been trying to kind of read this sort of slowly, but it's way higher than the level of statistics that I need even in machine learning. So yeah.
Thank you. The next question was your advice for those that are getting into the field of quantum computing and what you could have done differently looking back.
Yeah, great question. So I think honestly the easiest, easiest isn't the right word, but maybe the best way to get into a field, you could sit down and read a textbook. And I know for some people that's going to work better. But for me, I like to find a project. So like, and finding a project is hard. You need to know enough to figure out what you want to do. But maybe it could just be something simple like, write a simulation of Grover search or something like that. It's very, you can just choose something simple and concrete. And one of the benefits of doing this is that if you write some code or you have a write-up or something like that and you put it on GitHub, then that's something you can potentially use later. Like you can, if you're applying for positions or, PhD or whatever. So I think choosing choosing a project, a concrete project, and then trying to do it is good. And if you run into issues, that happens. Like I've chosen projects that I was like, oh, this seems easy, and then it was impossible. But I still learned a lot, and sometimes I sort of pivoted and so on. So I think that's very generic advice, though. So I'm trying to think about yeah, I'm trying to think if there's kind of more specific advice. But while I'm doing that, what could I have done differently looking back now? I think, I mean, there's so many things that yeah, it was a windy story, and there's a lot of things that I'm like, man, I could have saved myself like a lot of time. But I think the biggest thing, the biggest sort of, mistake that I made at a meta level, was not believing I could do something. And I think that the thing is that it's really easy to get into a kind of a mindset where we're sort of comparing ourselves with other people, and we focus on what it looks like they can do this, and I can't, or I'm not as good at X, and therefore I shouldn't. But I think if you find something cool, if you find something interesting, then just focusing on that is really good, and that will guide you towards, like, what skills do you need to pick up, and so on. And I think if I could talk to my younger self, that, like, particularly in high school, that's what I would say.
That's a great advice. All right. Next question is how do you gain experience after the necessary skills? And are there any internship, or what would you advise one to explore? Can we connect with you on LinkedIn? And then I think the question continues, is there a nexus between data analytics and quantum computing? If yes, what are the steps for a beginner?
Okay, cool. Yeah, so there's definitely, though, there was some great questions. Okay. So first of all, yeah, please feel free to connect with me on LinkedIn. I don't use it very much, but absolutely. Okay, and then so experience, yeah. So the Xanadu residency is a really good one, but there are lots of residencies out there. There's lots of companies. I don't know if D-Wave does residencies, but there's yeah, there's a bunch of residencies, and I would advise you to just see what's out there. Like, the only one I know about is Xanadu. So yeah, I think CERN has an internship as well. I'm trying to think if there's other places. Anyway, I'll have to think. I know that there's a bunch of them. But the other thing is, I think doing hackathons is good. Like, so there's lots of hackathons. I mean, like QHack is one hackathon, and obviously I'm biased, so I think it's the best, but there's lots of others, and they're great ways of kind of like you just meet people. You'll like, be on teams with people, and like you can work on a project where, like, you don't have to understand everything that's going on. That can be a really good way to just kind of like see how other people think, what sort of tools they use. I think that's kind of and it's social. It's like, it's not, I mean, calling it networking sounds cynical, but like really it's like these people could be your like peers, or co-workers, or whatever, and maybe you'll just come up with like a crazy idea one day and like write a paper, or like found a company, or I don't know, like it's a really cool way of getting into the field. So that's those two things, I think, because I mean, I know a lot of people will say go read papers, but I honestly think that in this like, particularly in this field, there's so many other ways, which have a lower bar, and like you can read papers, but and like a lot of papers come with like GitHub repositories, so go look at those. Like there's so much actual coding that happens nowadays. So I mean, I still read papers, like I'm kind of, because I'm a theorist at heart, but I think depending on what you feel more comfortable with, or what you like more, you can sort of incline towards that. Oh, okay, cool. And then, so Hamilton's question, is there a nexus between data analytics and quantum computing? If yes, what are the steps for a beginner? Yeah, so the answer is yes. And in a sense, I think this lives in the world of quantum machine learning. And as an example, there's a, so that the algorithm that that Netflix uses, or at least that it used to use, to make recommendations, was based on the singular value decomposition. So it's that's basically like sort of like taking a matrix and diagonalizing it, but the matrix doesn't have to be square, and there's various caveats. And it turns out that there is a quantum version of this. And so this was kind of one of the early papers on quantum machine learning. This is by Seth Lloyd and some other people. And so it was kind of exciting because it was like, wait a second, like there's things there was in this for the singular value decomposition, which is a very, very natural thing in quantum computing. It happens, it's a very easy thing to implement. And so it's surprising that there's kind of a way of doing it. There's a provable speed up. So people got excited about it. The problem with a lot of these things is that there's so many caveats about how data is provided, and like essentially like the architecture of the computer, and that's why like exploring all of the different kind of sub machines in the big machine that is machine learning, which includes data analytics, I think is actually like really cool. Like it's just such a rich field, and so much is not known. So I think the advice I would give is maybe find like actually something I found useful at the beginning was just looking at videos. So like there's a lot of content on YouTube. There's content from Xanadu, but there's content from Qiskit. Seth Lloyd gave some lectures. There's a bunch of random stuff out there, and that's easier to get into than much easier to get into than papers. And that will give you a sense for what is already out there and how people think about these things. But yeah, definitely for data analytics, this is potentially like a big application. So
right.
Let me know if that answers the question.
I guess it's not here. All right, thank you so much, David. There are many questions I still have that I wanted to ask you because I know you have a lot of stuff. But I want to end with these two questions. Throughout your journey, what were some of the biggest challenges you faced, and how were you able to overcome them? And lastly, where do you see quantum machine learning in the next 5 to 10 years, as well as specific areas that you're currently working on you'd like to share with us? These are just wanted to summarize here.
Yeah. Okay, great questions. So big challenges. So yeah, I sort of already touched on this, but self-belief is kind of like a big thing. That's been a big challenge. Like I think a lot of the time, so partly because I come from the school that I went to wasn't like it was like a very it was a pretty rough school. Like I wasn't really engaged. Like I had a lot of other personal challenges, and so I remember when I went to university, I was like, oh my god, everyone here is so much smarter than me. Like they came from completely different backgrounds, and I just felt very, very out of place. And it took me a really long time to kind of, and this is connected to making decisions that were just because like, okay, it feels like this is at least something I can do. So that's been like a really big part of my journey, just kind of saying, okay, well, this is something I can do. And like I think the way I've presented it, it's like, well, I chose this because it was convenient or because it seemed cool or whatever. And it's like that's part of the story. But a lot of the time it actually was really difficult to choose to do something because I was like, well, I don't think I can do that. Or what will people think of me if I do that? And so like just as an example, when I finished my PhD, I applied to postdocs, and choosing to not do postdocs versus going to Xanadu, and it was like I was going to go to Xanadu, and initially the focus was going to be on education. So like I didn't even know how to tell like friends or like my supervisor. I remember like I was like, well, how am I going to tell my supervisor that I'm not going to take a postdoc and that I'm going to go and like just like make interactive widgets or like something like that. It seemed crazy, and it was really, really difficult for me to make that decision, even though it was the thing I knew was right. So I think that's been one of the biggest challenges, and the honestly, like the way of getting over it has just been to kind of chip away at it and be aware that it's an issue. I think like knowing that the thing is a problem is like the first step towards solving it. Otherwise, you just make the decisions and don't think about it. So yeah, that's probably the biggest one. Okay, and then the question about quantum machine learning. So yeah, in 5 to 10 years, I mean, I think, and this is a really good question, because there's a lot of stuff going on at the moment, which I think there's a lot of exciting directions, but there's been this big focus in the field on basically provable quantum advantage. So you say, here, I'm going to introduce an architecture which does this task, and then I'm going to show that it does it provably better than a classical computer can. And when you say provably better, what we mean is subject to assumption. Like we can't prove that quantum computers are faster than classical computers, full stop. We always have to make an assumption about these oracles. So like essentially, like if you can provide the data in the following way, and there's a good complexity theoretic reason for this, but I won't go into it. I'll just say you need to have some way of supplying data, usually, and which is okay. This is a way of approaching things. But the problem is that these advantages usually involve like some asymptotic scaling. You say, okay, when A is big, we know that the quantum thing is better. And so the two problems are, first, you've made some assumption about how data is provided, which may be more or less problematic. Second, your results only work when n is really big. And we often don't know how big n needs to be. So like when you have these asymptotic kind of quantum advantage, it may not actually be relevant for the problems that you care about. So, and there's various other problems as well, like, I don't know, things that we tend to focus on in quantum machine learning that I think we're seeing are maybe dead ends or not as promising as we thought. And so like moving away from those, figuring out how to move away from those is, I think, really important. And that's why I sort of had this graphic of like a big complicated machine with lots of different things that people haven't really thought about. Because there's lots of cool things to think about that don't look like the existing approaches. So there's just really briefly, like two things that I'm kind of thinking about at the moment, that sort of step away from this sort of existing paradigm. One is going back to what quantum computers are good at in a very basic way. So like we know that quantum computers are good at basically using interference to do things quickly. So the cartoon of like quantum computers allow you to explore exponentially many possibilities, but in linear time. The problem is that at the end of that, you need to extract useful information. So how do you extract the information usefully? And the answer is usually interference. So like that's how, like all of the sort of basic algorithms like Deutsch-Jozsa, Simon's problem, Shor's algorithm all work this way. You have an exponential thing, and then you use interference to get only a few things that you care about, and that's how it works. So basically, just going back to that paradigm and saying like, how can we use that to do quantum machine learning? There are a few things at this which have this flavor, but they typically are more to do with formal results about proving quantum advantage, and less to do with actually doing quantum machine learning like proper. So that's a big thing that I'm thinking about at the moment. And I think another thing is with Penny Lane, like and sort of existing approaches, we tend to think about differentiable programming for the quantum part. Say, okay, like we're gonna kind of have a quantum circuit which does something, and we're gonna try and kind of differentiate this and optimize it and stuff. But a lot of what's interesting about quantum computing is actually to do with how we take measurement results and then process them. And so like thinking about how to it's kind of like it's hybrid computing, but of a different sort, where we now say, well, how do we optimize some of that post-processing? And there's lots of examples, like like a very simple example is if I want to take some say like I can do like a Fourier transform from like the energy domain to the time domain, some Hamiltonian. And then I want to kind of like take some samples, some finite number of samples from the time domain, and use those to learn something interesting. And this is like a very concrete problem, actually, a real problem. then people have proposed a bunch of stuff, but we don't really know what's optimal. It's very difficult to prove that things are optimal. And in practice, what you probably want to do is use machine learning to figure out what's optimal, or to explore the optimization landscape. So those are two things that I'm thinking about at the moment, which are I think a little bit different from sort of current approaches, and that I hope, I mean, who knows, maybe not, maybe relevant in 5 years' time.
Thank you so much, David. It was really great having you today, and I'm sure everyone enjoyed your talk. We hope to invite you sometime in the future. For the moment, we say a big thank you for coming. And thank you to everyone who made our time to come here and join us in this talk. Thank you all, and I hope you have a wonderful time.
Thank you.
All right. Bye.
All right. Thanks, everyone. Thanks, David. Thanks, Gideon. Bye.
Yeah, bye.